Yeah. Yeah. Exactly. Exactly.
You should be good.
Hello, good morning. There's a homework 6 that is included for the exam, but it's due. Officially, it is due on the day of the exam itself, but like let's say 24-hour or buffer. That I like to say. The structure and the style of the exam would be the same, how you want to study for it, most of it remains the same. Homework, problems, like central or lecture examples. The second, both are equally weighted. And if you think those are not sufficient database, then you go to the textbook, worked out examples. And if necessary, the problems at the back of it. Any questions or comments on that? Come again, some. Was there any comment or question on the? We introduced the idea of a magnetic force. If there is a charge, then it experiences an electric force. And now we are talking about a new concept that if there is a magnetic field that experiences a force because of the magnetic field also. There is an electric force. And that's charge times the electric field. Electric field itself could have been created by another charge sitting somewhere. It might be very far away. But what's relevant is that if there is an electric field, there is an electric force on it, very much like gravity. If there is a gravitational field, quantity that we usually learn is 9.8 meters per second square. That's called a gravitational field or the acceleration due to gravity, since it is very much remain the same, very close to the surface of Earth. We think of it as a constant. In general, it need not be constant. Similarly, instead of a mass, if you had a charge, it is charge times the electric field. Gravitational force is mass times the gravitational field. And here is the electric field. The electric field is created in a scenario, but here we are saying if there is an electric field, there is an electric force. Now we have introduced the idea of magnetic force. And that's equal to B now. Sometimes we drop the subscript B there, presumably means that there is no distinction between the two, but be careful with that. Remember that when we were doing forces in mechanics, then we had to identify the forces. One of the important steps in that was to identify which force it is. So this is one particular force, and now we are learning another type of force. And here, the way to look at it is that it is not a charge that is important as far as magnetic field goes. It is a moving charge. Moving charge means Q times the velocity. It is moving charge, that is Q, and the movement is described by the velocity. And cross vector, this is a vector. Force is a vector, so I need to construct a vector to have a force. So that's the cross product of the velocity and the magnetic field, or the moving charge and the magnetic field. And B here is the magnetic field. Of course, there is a gravitational force, which we presume is the most elementary one, but it turns out at a more advanced level, that turns out to be the hardest to understand. So that has force of gravity G that's equal to mass times G. So G is the gravitational force. If you have a mass, if the object doesn't have the property of mass, then it will not participate in the gravitational force, or the gravitational force will not act on it. But it is the G that plays the important role. Force is mass times the gravitational force. And pretty much, if you have a gravitational field, mass just flows along the direction of the gravitational force. This is just a number multiplying that gravitational field. Same thing with electric field. There is an electric field already existing, and the charge just multiplies that electric field. It flows in the direction of the electric field. But now the magnetic field is completely different. There is a magnetic field, but the force which decides the direction of acceleration, that's not in the direction of the magnetic field or in the direction of the velocity or the motion of the charge. It is in an entirely different direction. In fact, it is perpendicular to both. The cross product of two vectors is perpendicular to both the vectors. So the two vectors form a plane. The two lines, two vectors means two lines. Two lines always form a plane. The cross product will be always perpendicular to that. So if you have a charge Q times V, and there is a magnetic field in general, so that's your magnetic field, but magnetic field is not a vector, it is the field lines of the vector field, so you have to think of it like this. That's your magnetic field lines, and there is a charge moving in this direction, then not necessarily in the direction of the magnetic field. And the force it will experience will be out of the boat. So Q, then the right hand, so you point your fingers in the direction of the first vector, then you try to rotate it about the axis and point your palm in such a way that magnetic field is facing that palm, and then you open your thumb and you see the direction of the force. So the direction of the force is coming out of the boat. If it was a positive charge, if it was a negative charge, how do you go about it? You just flip the direction of the force. You calculate it using the right hand rule, and then you flip the direction of the force, and that gives you the direction of the magnetic force. In this case, if it was moving this way, it will start accelerating in the direction coming out of the boat. If it is accelerating in a direction perpendicular to the direction of velocity, there is a circular nature to that motion. So this will start turning around. At least for a moment, it will turn around. And in this case, we have shown that in the magnetic field case, there's a circular motion. So the circular motion means that it goes around the circle with respect to the magnetic field. So that's your magnetic field. So this is going this way. It seems like if I go in this direction, no, that's not the way it goes. There is a perpendicular component to that. The parallel component does not bother at all. So it is a perpendicular component of the velocity and it goes in a circle in the plane perpendicular to the magnetic field. So moving charge goes in a circle in a plane perpendicular to B. You might ask, what does this velocity, the parallel component along the magnetic field do? That makes it drift. The acceleration is purely in this direction, so it makes it drift. So it is going in a circle, but it might drift. That's what we talked about. Charges coming from the sun. They not only go in circles, they also move around in the direction of the magnetic field. And that leads to a helical motion. So that is circular motion, and you make a drift to that. So the charge is moved this way. And that's because if that is a parallel component to the velocity. The velocity was perpendicular to begin with, then that drift is zero. What if the charge was in the direction of the magnetic field itself? If the charge was moving in the direction of the magnetic field, what will be the motion? What will be the direction of the circular motion? In which plane would it be? If the charge was moving in the direction of the magnetic field, let's all begin by saying what is the magnetic force? No. The big class who wants to answer. Predict that.
Can you rephrase the question?
So there is a magnetic field. So let me rephrase. That's a magnetic field. That's B. A charge is moving. I said magnetic force acts on a charge that is moving. Correct? So that's your velocity V. But it's in the direction of the magnetic field. What's the direction of the magnetic force? Right? We said that the cross product of these two vectors gives you the magnetic force. What's the cross product of V and B in this scenario? Cross product.
Zero.
It will be zero, right? Because cross product involves a sine theta. So that's counterintuitive because we expect that it's moving in the direction of the magnetic field. Zero. So that's the counterintuitive nature of the magnetic force. That's magnitude wise. So it is equal to Q times V times B. And sine theta, where this is the angle between V and B. The angle between them is zero, sine of zero is equal to zero, and that is the reason why there will be no magnetic force on a charge that is already moving in the direction of the magnetic field. So if you want to shield yourself from a magnetic field, flow in the direction of the magnetic field if you are a charge. Right? If you want to shield the charge moving from the magnetic field, you just move it, make it move in the direction of the magnetic field. That's not the usual case with most of the folks. We also talked about if it's a circular motion. The properties of the circular motion is what the time period. Instead, we talk about cyclotron frequency, and cyclotron frequency, sometimes like a subscript C, but it's the natural frequency of the moving star. And that's equal to Q times B over M. It plays a central role in magnetic effects because it is directly proportional to the magnetic field. So if you know how frequently it's moving in a circle, then you know the measure of the magnetic field itself, proportional to that. What's the radius of the circle in which it is going? That depends on the velocity divided by the frequency. Now we wonder, is it the total velocity or is it only the perpendicular velocity? So let's call this the parallel, and that's the perpendicular direction. So the component that is perpendicular to that is matters. This is the perpendicular component. In your homework, you explicitly see where how the circular motion comes by, and hopefully that helps. Here, I want to do examples, and mostly that also means that there are applications, like how do you use magnetic field. Remember, first we learned gravity, and then we found applications of that. Don't you know that basically you can predict things, or you can control stuff based on how things move or fall. You can control stuff. A classic example is how you throw a stone up in the air. You can control really based on the initial condition where exactly things will fall. What does electric and magnetic field do? They mostly act on charges, and the charges are typically small, like those easily accessible charges for atomic in atomic incisions. So basically electrons and protons. So we would like to control them. And now we have learned a new way of controlling them. Electric field was a simple control, it's in the direction of the field itself. Now we have two forces that we can control, so we can start manipulating, and that really brings in technology in there, and you can get very clever once you have two forces, and you can do various stuff. So one of the things in atomic physics is you might want to control the velocity of a charge. Like we're really thinking of atomic particles here now. Let's say there are atoms and you ionize them. How do you ionize atoms? You basically put them in a small, once it like atoms are really tiny, so you cannot pick one atom. That's usually very hard. So what we can do is play with the whole set of atoms, so that statistical set of atoms, and they're all moving randomly at various speeds. Like for example, if you take a gas of atoms that's there in this room, one of them might be going extremely fast, and the second one might be going extremely slow. They're statistically distributed. But you would like for your experiment to have a set of atoms which all have the same velocity. Like that might be a requirement you have. So how do you do that? So here, using electric and magnetic field, we can basically set up a configuration which will give us that feature. So let's try to see that. So let's so this is called a velocity collector. So let's think of a gas. So this is the, before that there is a cylindrical chamber or rectangular chamber. And when we say we want to control things, what are we talking about? We are having an atoms. So take a small cube. You don't want the whole room size set of atoms. Typically it is 1 centimeter or even less, or 1 millimeter or so in size. The sample is just a gas filled within a 1 centimeter cube box, right? So that's a box, and then you want it. Let's say that you want a very high velocity, so you will heat it up. Like how do you increase the velocity of atoms? So basically you heat it up, and so the heat, you heat up very simplistically speaking, and they all start moving faster and faster. They heat up, but they're all going in different directions, and that's what we want to control. We would like to pick a velocity out of it. And a simple way of controlling the velocity without using any electrical magnetic field. Make a small hole in the container, and they will all start coming out of that hole, but they will all go in different directions. Not only go in different directions, they will. In each direction, they will have a whole spectrum of velocities. One might be slow, one might be faster, and we cannot really see these atoms. The only thing we know is that they are all moving in a certain direction. Now, how do we select one out of this? Again, make it very simple. We just make another hole. This is a filter we are talking about. So atoms come out of a hole, and then you make it go through this. So you're basically lost about 80% of the atoms, but still there are plenty of them, and they are all going in this direction. And put another hole there, and you can be pretty sure that only those who are really coming straight can be going through both of them. Still, there will be an error there based on how small these holes are. There will be a small beam size, so it might really spread out a little. You cannot help that. So, nevertheless, you have within about 1% accuracy, you can say that the velocity is all going horizontally. When you heat it up, another advantage you have is that they are getting ionized. Either you can heat it up and get it ionized because they are hitting each other, they tend to lose electrons, or there are other ways to ionize it. However you do, they are already charged atoms. They could be large in size, like silver atoms are very easy to work with. So take an atom which is in the size of silver, make it in the gaseous form, and then make a small hole. Sounds reasonably simple at least conceptually. The only thing might be that these are small distances, so you have to calibrate and be very careful with the experiment. Precision is what matters here. Now, what we have is that this line represents a lot of atoms. It's not one atom, it's not one charge. Lot of them, 10 raised to 23 of them. They're all moving in the straight line. They have a velocity v, but that velocity v might be changing. One might be going very slow, one might be going very fast. And our goal here is to select only those who are going with a specific speed are allowed. So this is going to be a filter, which says that if you're on the right hand side, anything that goes with 3 meters per second, 3 meters per second plus or minus within 1% will come out of that tube. Rest everything will get blocked. And how do you do that? Again, it will turn out very simple. So we have our two forces to control. Let's say we put a magnetic field. By the way, whatever we are saying is we need to have an intuition for what this is all about. Recently we have flat screens for TV. Only about 20 years back, there used to be this huge monitors, which you might even now see around, and they were called cathode ray tubes. And this is nothing but a basic idea of that. This is how, so a cathode ray tube, that's one thing that you see around. Basically, this is the beam you control. So that beam can be moved. You can scan them wherever you want. You can hit them. So that's the way a basic television screen used to work. These days, we can control each element or each pixel on that screen, so it's controlled straightly. But this still has a lot of applications. So that's the magnetic field. And the uniform equal distribution of lines means that it's uniform. That's your B, right? So B is going into the ray. And these are all, let's say, positive charges coming in. The only difference between different charges, there are 10 raised to 23 of them. The velocity is distributed in the sense that it might be all very slow and very fast. But they're somewhere related to this temperature. How do you typically associate velocity with temperature? How do you associate temperature with velocity? Anyone? Check on how you. That's correct. As temperature goes up, velocity also goes up. But a rough relation. Proportional or velocity square. There's a kinetic energy that is equal to the temperature. So reasonable. So and here compare energy. Temperature is an energy which is controlled by K, that is a Boltzmann constant that gives you the amount of energy that is associated with temperature. And here there is motion, just equate that to half mv squared. That's typically more like that could be an x direction motion, that could be y direction motion. So there could be some number in there, so maybe 3 times or something. Let's say, let me just say 3 times. So it could be more degrees of freedom in the sense. For each degree of freedom, you get a temperature equal to half mv squared. Kinetic energy is equal to temperature. So that's something you want to keep in mind. So you heat it up, how much you heat up decides what is the velocity, but that velocity is statistical. It's an average velocity we are talking about. And what the goal here is that this average velocity is spread out around this temperature. Around this temperature means temperature has a specific average velocity. Around that, it might be a huge spread. It might be all the way to very close to 0 and all the way to very large. But most of them, 90% of them will be very close to this average velocity. But we want to be very selective and we want to specify that velocity much more precisely. What happens to this positive charge? This is moving with velocity v. So this positive charge now here, once it enters the field, it's right here itself, it experiences is that it experiences a force. So that's your velocity v, and it experiences a magnetic force. Now, how do you see the force? That point the 4 fingers in the direction of velocity, that's your first vector. Move it around so that the palm is facing the magnetic field. Open your thumb, the direction of the magnetic force is upward. If it was a positive charge, it is stays upward. If it was negative charge, you flip the answer. So the magnetic force is upward. That's your magnetic force. If there is a force, if that was the only force acting on it, then it will accelerate in that direction. So acceleration, velocity is going this way, acceleration is perpendicular to that. Think of circular motion. When Earth is moving around the sun, velocity is tangential, acceleration is radial. So the same idea here, velocity is going in the horizontal direction, here in the direction of the cube. It is getting accelerated or experiencing a force towards the plate or the cylindrical surfaces. That means it will accelerate in that direction. That means it will start going in a circle around that. So it will actually bend. So that's very intuitive. You pull someone, it gets bent. If you're already moving there, it starts moving towards the direction of the force. So this bends, and eventually they all go and hit the plate. So if this was long enough, so all these positive charges, if you don't do anything else, so they will all go and hit here, right? So that all the positive charges will come and collect here. That's a conductor. So if all the positive charges are there, all the negative charges will come in here. Right? Just because there was a magnetic field, they got drifted in a sense towards one side of the cylinder, or let's say this is rectangular. So you have positive charges here in a few minutes. To begin with, they were neutral, and negative charges in here. That means there is an electric field now. Once this has started collecting, the new positive charges do not want to go there. Right? They will repel the next positive charge. This is, remember, statistical. The first one had a free go because there was no one resisting it. Very soon there are a lot of positive charges sitting there, and they say this is already full. We don't want any more positive charges here, so they repel them. So that's because there is an electric field in here. So that gives you an idea that, oh, so that's going to repel anyway. So what if we actually provide that electric field? So instead of doing this, that we wait for it to collect that, let's provide an electric field. Electric field is in this side. We provide an external electric So what are you doing? You have a small box, you heat it up and think of an MRI machine that creates this magnetic field. It can create a very huge magnetic field, but typically for these kind of experiments, we need much smaller magnetic field. A small this size magnet is sufficient. So you have created a magnetic field, and the electric field is just to provide a battery. Using a battery or a higher power supply, you can create an electric field. That's the idea of a voltage. And you can create forces in this direction and forces in that direction. So a positive charge is experiencing a magnetic force in the upward direction and electric force in the downward direction. So earlier, they were all getting drifted to the right side, but we said, oh, electric force will make it drift to the bottom. The others were pulling it, magnetic force is pulling it up, electric force is pulling it down. But what decides this? Like, how does these two forces depend on velocity? So we already noticed that the magnetic force depends on the velocity, and that's what we want to take out of this. We want to cancel these two so that they don't experience the force at all. They go through the whole cylinder. That will happen only if these two cancel. And let's see how they will cancel. So let's try to cancel the force due to the magnetic field. Let me say the magnitude because they are in opposite direction. That's equal to, or actually, let's use Newton's law. So there are two forces acting. So Newton's law will tell us that mass times acceleration is equal to the vector sum of the two forces. That's force due to magnetic field plus the force due to electric field. You've not been using that form of writing for some time because we have only one force in hand. When you talk about charges, there's only electric forces. But now we have two forces. Now we can manipulate things. And now let's ask, we do not want it to curve, so acceleration has to be zero. So when will A be equal to 0? So we do not want it to be accelerating. That means they have to cancel each other. They are all in the same direction, so we can just worry about the signs alone and what. So FB is plus QBD, right? It's Q times B times B times sine of the angle between the two vectors contributing to the force, velocity, and the magnetic field. Velocity is in the point, magnetic field is going into the page, angle between them is 90 degrees. And the force due to electric field is going downward, so it's Q times E. Acceleration is 0 because we would like it to go straight without getting deviated in either direction. And this gives us a relation that is Q, V, and V sine of 90 is 1, that's equal to Q times E. Notice that the charge cancels out. So you might worry that since we really don't have control on the atom, all these atoms may not have the same charge. Some of them might have one positive charge on it, some of them might be extra ionized that can have two positive charges on it. So the total charge doesn't matter. It's like the gravitational case of something falling under gravity. The mass cancels out. That's a very special scenario. And only in the special situations does that mass cancel out. Only for gravitational effects does that mass cancel out. Here, the charge cancels out when there is both electric and magnetic field coming into picture because both are proportional to the charge. And we are saying that velocity V is equal to E over V. That's the requirement. So if you set up your electric and magnetic field ratio in the way that that's equal to velocity, the ratio of electric field to magnetic field is exactly equal to the velocity, then that will directly come through, but then we said that earlier, there was a whole distribution of them. If the velocity was larger than this selected velocity, then the magnetic field will win, because velocity depends on the magnetic field. So larger velocities go this way. So larger velocity. And slower ones, faster, slower. So you set up your velocity selector based on E and B, and if you go faster than that particular velocity that you chose, it goes and hits on the right side. If it is slower, it goes and hits on the bottom plate, and what you get out in here is a beam now. This is a beam of similar velocity. So we have selected the velocity, and that's what is called a velocity selector. So earlier you had a source of atoms which are all moving, but now you have a technology that you can say that I can provide you with a beam of atoms which all of them have the same velocity. What can you do with it? Next time you're doing any other experiment, and if that experiment requires a very specific velocity, or you want it to provide a particular velocity, you can provide that. And one of such an experiment is a mass spectrometer. A mass spectrometer is a device that allows you to measure the mass of an atom. Right? One would think that is very hard, like atoms are really tiny. How do you go about measuring the mass of an atom? You cannot keep it on a balance, you cannot weigh it on a spring balance. So you use techniques like this, right? We can control them, and what they do under these forces, besides or we can think of an effect, we can get clever and measure the mass. So let's see the idea of a mass spectrometer. And mass spectrometer are a very common device in most of the technology spaces, because the measurement of mass is so important. Most of the labs that you see around in our university probably has a mass spectrometer. They're usually very expensive. What decides the price is how accurate it can be. If you want the mass to be given in one significant digit or two significant digits, that will be a reasonably cheap one. If you want three significant digits or four significant digits, it can very easily go into billions, like not just millions. It can cost you billions, and it might be only one in a country. Like a certain country might have only one mass spectrometer, which can really measure precise mass. But for most purposes, we can have a mass spectrometer that's available in a research lab, but still expensive enough that we cannot have it in a garage setup where you can play around with some experiments. So this is a mass spectrometer. Many of you might have already used it. What's the spell? That's R. See, when it's so close to the board, it doesn't help to depend on visual instinct. Is that correct, sir? Good. Okay. Okay. So, how do you go about measuring the mass? Again, the idea is very simple, but as I pointed out, it's one of the most expensive instruments out there. Like MRI. MRI is a very expensive instrument, but this is a lot more expensive. Have a magnetic field. This is a boundary, if you want, where the magnetic field can be stopped. All that becomes a challenge. How do you stop the magnetic field at one point? What's a magnetic field be? MRI is a device that produces a huge magnetic field, but typically mass spectrometer needs much smaller fields. As I was quantifying both in here, and we already have a velocity selector. So we make this sample where we heat things up. This is a gas, right? So that's the whole thing. And then this is a velocity selector. So this is a velocity selector. What that means is that we know exactly what's the velocity of the particle that is going in. And so I know that there is a positive charge. So first you ionize them, then you have to select the velocity, and that particular charge with that particular velocity goes into a magnetic field. That's your V. Notice this already has a magnetic field, and this already might be having a magnetic and electric field. So, there are two concepts coming together. Often you will use the same field for that purpose, but conceptually speaking, you have a velocity selector. Now you have a charge Q, a moving charge moving with velocity V, and you make it go through a magnetic field. So the moment it enters the magnetic field, what does it do? What does the moving charge do in a magnetic field? It starts going in circles. That's all it does. So it has to go in circles. So which direction a circle would go, this way or that way, right? So use your right hand rule, and this is your direction of V, and it can twist around, but you face your palm in the direction of the magnetic field. Magnetic field is going into the hole, palm is facing in, open your thumb, and the force is in the left direction. That means the circle for a positive charge will go this way. So it goes in a circle, and that will be the circular path. So that's a circle of, so this is a semicircle, and right after coming here, it starts going straight, right? The force goes away. If there was a magnetic field everywhere, it would have taken a circle. So it makes a semicircle if you want, and there is a radius after that. And that radius is absolutely decided by the velocity. Remember, we said that the radius in a magnetic field was decided by the velocity over the cyclotron frequency. I said cyclotron frequency plays an important role. How frequently does it go in a magnetic field? In this case, it is only one circle, but then it takes a certain amount of time to reach that. That's crucial, and that's decided by omega c, which is called the cyclotron frequency. Cyclotron frequency of Q over M and B. That's your mass, right? That's what we want to measure. That's equal. B is now fixed because we have chosen the velocity. That's the velocity selector in, and this is Q over M and B. We are interested in the mass. Right? We want to keep rest everything the same. So mass goes in the numerator. The mass there. That's equal to R times Q times B over V. I keep my magnetic field the same. Charge has to be kept same. What that means is that in this velocity selector and into this whole process, you cannot afford to have a different charge. If it is singly ionized, you want to keep it singly ionized. And that again can be, we can use a filter to select them if you make if there are one charge or two charge, one experiences an extra force. So that's possible to do, but you have to make sure that that is already done. So Q has to be the same in this beam. So this is a beam, remember, it's not one atom, it's a whole beam of atoms. They all have the same charges, they all have the same magnetic field, and they all should have the same velocity. That's why the velocity selector plays an important role. And once you have that, the mass is completely determined by the radius. So if I were to have a detector here of atoms, what is a detector of atoms? How do you detect a tiny set of atoms which are 10 raised to 23 number? This could, for example, this could be silver atoms. Silver atoms come and hit a plate, a photographic plate, it leaves a small white spot there. So that is how we detect. So any kind of detector that can sense these charges. We don't depend on photographic detectors anymore, so there are more sensitive detectors here that can select where it is. So you just have to, so these days in a mass spectrometer, you can put a lot of sensors. And you just have to make sure which bin does it come and get detected in. Based on that, you have measured your radius. If you have measured your radius, you have measured the mass. I should point out so that's the expression for a mass spectrometer. You design a mass spectrometer. How easy it is to make it, that is very challenging and it turns out to be very expensive. I should point out if you have already worked with a spectrometer, this expression may not look very familiar. It looks different because I have done this in two stages. I've already selected that velocity. So I'm writing this expression in terms of a selected velocity. Typically, a mass spectrometer, the same magnetic field is incorporated in the velocity selector also, and the velocity selection depends on the mass too. And that mass shows up here, and there is a second, so there is a V here, but V also depends on the mass, but they are not exactly canceling out, so there is a m raised to power 3/2 or 1/2 that will show up. That you will see in your homework, but just be careful that whenever you're working in a lab or if you ever have to use the mass spectrometer, which most probably all of you will use at some point or the other, then make sure that this expression for velocity is simplistic in the sense that we have assumed that the velocity is already selected. Any questions on that? Any comments? We have, if you want, try to control charges here. Now we want to go in a slightly different scenario where, or another way of saying it is that instead of saying another scenario, we have a beam of charges here. That's what is happening here. There's a beam of charges, which is a flow of charge. There is another place where you see a similar scenario where a lot of charges are moving, and that's a current carrying wire. A current carrying wire has a movement of charges, a flow of charges. So whatever happens to this beam is going to happen to the electrons that are moving inside that wire. So you can expect that if this was a wire and you put a magnetic field on that, all the charges will go on one side of the wire. And we never expect that inside a wire, how are the charges moving? Are they moving on the left side or the right side? It's like a traffic. Like, do you drive on the right side or the left side? Electrons in general go wherever they want to, but if you put a magnetic field, they actually go towards the upper end. But I should add one more thing that one could ask. This is a generic statement here. I don't think I have emphasized those points here so much in this course, but it's expected that you know from this course that if you have an electric wire, can the charges move at the center? One would expect that, especially copper is relatively expensive. If you want to transmit power from one state to the other, that's a lot of copper wire. And the price of that copper itself decides whether you want to use copper or you want to use another metal. So the amount of copper you use plays a significant role in the economics of transmission of power. And you could ask, do the electrons really go inside that conductor? Remember that we said charges always stay on the outside part of the conductor. So when the electrons are moving in that wire, do they move on the outer part of the wire or do they go through the central part of the wire also? And the answer is no, they do not go on the central part. They mostly stay on the outer part. So you can save money if you can design your wire, which is there only on the outer part, so use some plastic inside and put metal on the outside. That might require some design, you have to fabricate it, that will cost some price, but at least the price of the metal has come down. So that's one feature. So when I said that they will move around that way, that uses that fact that they are at the center, but usually they're already on the surface. But if there was a flat sheet, if this was a flat sheet, right? So there was a planar metal, and there's a current going through it, they will all drift to one side. And that is usually observed, and that's very common. So anytime you have a electric wire, wherever there is a current, that's a beam. Right? The beam is very identical to a current. So let's see the quantity that relates that. So magnetic force, let's say moving charge, is the same as current. A flow of moving charges. So we're talking about a beam now. It's basically a current. How do we see that? Simple words, so that's Q times velocity. That's your moving charge. What experiences the magnetic force? A moving charge. Q times velocity. It's not Q alone. It has to have the motion also has to come in. But that's equal to, let's say this is Q. Let's write this as Q over delta T. Velocity has delta X over delta T, like the path it takes, but if it's a wire, then the element of wire decides how far it will go. Right? If the wire is curved, the delta X is curved. This is nothing but current. If that's your current, and this is your DL. So let's say you're going to make this differential now. This is I times let's say one is differential let's say small charge. We will make it small charge dq, and then this becomes dl. X. So if you have what it means is that if you have a current carrying wire, that's an I. The direction of the current is what is the direction of this length. When you say a line element, usually it is not clear it is that way or this way, right? If I have a current carrying wire, what do you mean by the direction of that? That is decided by the current I. So the direction here, even though we have put it on S, it is actually decided by I, and the length here is this, that's going to be S. Where the direction for that length is coming from the direction of the current. So a moving charge, which we kind of interpreted as a beam of charges, a flow of charges. That is another way we can realize that. A much more easier way to set up in the lab. That's a current carrying wire. So a current carrying wire should experiences the same kind of forces or the same kind of analysis goes through for a current carrying wire. So for our purposes then, so magnetic force on a moving charge, we said. That's equal to V equal to Q V cross B. That's the same statement as earlier. Now we generalize this. Magnetic force on a moving surface, on a current carrying wire is equal to, if there is a magnetic field, it will be Q times V replaced with the current, right? I this time times VL cross with or the S at the S. Oh, change it to L. By now, hopefully we have started recycling words whenever we want to use a different letter. Same idea. And B, that's a small, tiny element of wire. So you want to talk about a small, tiny element of force, right? If you add up all these forces on this tiny elements, so break the wire into tiny elements and calculate the force on each of them, and you can get the total force. Just the simple idea is to replace a moving charge, the concept of a moving charge, with a current times length, and now you have the same tools to calculate now on a current carrying wire, and that current carrying wires are easy to handle, so you just make a wire and find the force. These forces are typically small unless the magnetic field is really close. For example, you can ask when you have a current carrying wire that is transmitting power from one state to the other, that is gravitational, Earth's magnetic field is always there. So they should all be pulled towards one direction. That's true. They all experience the force, but this force is typically small. The magnetic field due to Earth is relatively small compared to an MRI. An MRI magnetic field is 10 raised to 1 Tesla. Gauss 10 raised to 4. So that's MRI. Earth's magnetic field on the surface of Earth, that's 10 raised to -4. Yes, there is a magnetic force every time you're close to a power line, but they are really tiny. And anything moving, remember, exaggerates this very much. So we will later talk about if there is a current carrying wire, it also produces a magnetic field. So if you're close to a power line, you're exposing yourself to a magnetic field again. How big is the magnetic field? There is a magnetic field around due to the Earth. We create magnetic field, always you have to ask how big is it? If it is in the third significant digit, then we do not have to worry, that doesn't affect our calculation or our understanding too much. So let's do an example where we see a magnetic force on a current carrying wire. So let's have a let's have a triangle because rectangle is kind of slow. This is a current carrying loop, and that has been set up in the shape of a triangle so that you can use the geometry of a right triangle. So that's a current I that is flowing through it. When you have a current flowing through just a wire, I mean that there is some battery somewhere. So there's a current carrying loop of wire. And you immerse this in an electric field or magnetic field. And let's have the magnetic field in the diagonal. Horizontal. A various configuration you can think of. You can think of magnetic field being in the plane, like I have shown. It could be vertical. It could make an angle. It could be parallel to the diagonal line here, or it could go into the board. It could come out of the board, and various configurations possible, but the analysis is reasonably similar. So let's say it is A, B, and C for the language or for vocabulary, so that we can talk about which side we are talking about. That's a magnetic field, and we would like to ask, is there a magnetic force on it? So that is a loop of wire you have placed, and Earth has a magnetic field already available to us. We are just saying that what is the force exerted on this loop of wire due to the magnetic field of Earth. So this could be the Earth's magnetic field. Let's calculate the force on AB. So let's say force on AB, on the side AB, that's the magnetic force we are talking about, and that's equal to I times, we need the length now. So this is length, the length of AB crossed with the magnetic field, which is going to be horizontal. So let's say this is your X, that's your Y, and Z is coming out of the board. And let's say B is then X hat times the direction of B, and let me put in a number. Let's say 2.5 millitesla. A typical refrigerator magnet will have that much of magnetic field. And let's say LAB is, this could be a loop of wire. It could be the size of your palm. Let's say about 2 centimeters. 2 centimeters, and let's take a 3 that I can use right triangle properties. And let's say LBC could be 4 centimeters. That's your length, and I want to put a current also, right? So current I could be 1 amp is easily possible in a lab setup. So relatively high current. Usually the batteries give you in milliamps, but let's say that's 1 amp. So we calculate the force on this side alone, on this element of that loop. The 3 loops, there will be 3 forces. First, let's calculate the force on this edge of the loop. Right? There are 3 sides to a triangle. We find the force on one of them. What's the direction of the force? Let's calculate the direction to begin with. LAB. So that's direction in this way. That's your 4 fingers pointing in the direction of the edge. The magnetic field is in this way. How do you rotate your hands so that magnetic field points or the palm points in the direction of the magnetic field? Try to point your fingers in such a way that it could be tricky. What's going on? How do you point your palm in the direction of the magnetic field when your fingers are pointing in that direction? What's going on? They are not, but how do you feel? So what is happening? How much is the force on that? 0, very good, that's all, that's why you're not able to point it, right? That is no direction, sometimes when there is no magnitude, there is no direction, so all your roots for direction fail because it's 0. 0 doesn't have a direction, very good, right? So this is 0. So you don't even have to talk about the direction. When you do this, that's something you're not able to do. So I could be 0, so there is no force on this element, there is no magnetic force on that. Good. Let's do the other side. And it's 0 because it is in the direction that electrons are flowing in the direction of the magnet, not in like the opposite direction of the magnetic field. It's sine of 180. Let's just to clarify, the magnitude of FAB is equal to I times LAB times B times sine of the angle between these two vectors. They are anti-parallel, so it is 180 degrees. So that's equal to 0. Like that's why, and once it is 0, then there is no direction. So we started with the direction, so we got I got it. Okay. So we have let's calculate our other forces. So let's do force on the side BC. Force on the side BC. Same current that is flowing through, it's a loop. But the I times this time the length BC, but the direction is going from C to B, right? Keep the direction of the current dictating your length L cross with B. And that equal to maybe either X or Y, right? So let's write this as L, I times LBC in the direction of minus K hat. That's one way of doing this. Cross with magnetic field is in the direction of X, that's I hat or X hat times B. But the direction is given by this minus J cross with I. J cross with I, so that's in J, but it's minus J, that's pointing in this direction. And you want to fix it so that your magnetic field is facing the thumb, and you open your thumb, and it is coming out of the hook. Going in, facing the magnetic field, and thumb is coming out. Sometimes here the board is fixed, so you cannot move it around. You have the ability to move your notebook, so you don't have to twist your hands or move your notebook. Sometimes that is helpful. So that's it. I recommend it. So it's coming out of the board, that's Z hat. And for these two, so minus, this is Z hat or K hat. Either way, Z hat. I keep interchanging between Z hat, K hat, X hat, and I hat. It doesn't matter. So that's equal. It's coming out of the board, Z hat times I and L B C times B. Oh, what's wrong here? There's no direction. That's been accommodated for here. No direction. So that's the hat. Current we said is 1 amp. Length we said BC, that's 4 centimeters into 10 raised to minus 2. And the magnetic field we said is 2.5 millitesla. That's 10 raised to minus 3. So 2.45 into 4, so that's 10. And 10 into 10 raised to minus 5, that's 10 raised to minus 4. So that's we have times 2 sig digits into 10 raised to minus 4 newtons. So this is a reasonably big size object. We are not talking about the atoms anymore. So this is a current carrying wire of 1 centimeter or 3 centimeter length, but the force is relatively small, 10 raised to minus 4. Very used to when having physical objects around, we work in units of newtons of the order of 1. So it's relatively small force, but nevertheless, there is a force. And now let's try to calculate what is the force on this? Right, on that the force on the side AC is equal to I times length AC cross with B, and that's equal to I times length is in the first quadrant, right? This length, if I were to think of it as a coordinate system, this is in the first quadrant. And that will be equal to the magnitude L AC times that is a vector associated with this L, which will be, let's say, the sine of theta, or I can bring in an angle right here. Sorry. I just need that angle, so it's L AC times B times sine of the angle between the magnetic field and the L, theta, times the direction, which is now again use your right hand, and this is your direction of L. If you want, and you want to face the palm to face the magnetic field, so you don't want to keep it like this or like this, so you want to have that in this way, and you open your thumb and it goes into the page. So it is minus V hat. So the direction is minus V hat. Plus equal to minus V hat times current is 1 times 0. The length we said is length of AC. So let me do this in two steps. Take the room here, so I times B and L AC times sine theta. And I wrote that so that they combine together in that form. That's your line L AC times sine theta. So sine theta is this. Sine theta would be the length of this hypotenuse projected on the vertical side has the sine theta out. So this quantity is nothing but LBC. Remember, if sine theta is L BC, BC, yes, LBC over LAC. So these two is nothing but LBC. IB times LBC. I'm specifically writing it in that form to bring out a point that this is nothing but the same as down here, but with a negative sign. That's equal to minus V hat times the same number. You can put in the number, it will come out the same because it's the same number. 1, 4, and 2.5. So what's the total force acting on this loop of wire? It's plus 1.4 and minus 1.4. That's equal to 0. You might think that it is a coincidence that I chose these numbers in such a way. No, it is not a coincidence. A current carrying loop of wire in a uniform magnetic field always will have 0 force on it. This is any loop of wire is a magnetic dipole, like an electric dipole. Any current carrying wire is by definition a magnetic dipole. A magnetic dipole in a uniform magnetic field experiences no force. But what else will it experience? An electric dipole does not experience a force, but it experiences something else. Like if you have a positive and this is an electric field, if you have a positive charge and a negative charge, what's the total force on this? That's zero, but what else does it do? It is does something else. It twists. The forces cancel out, but they rotate. The same thing now with a loop of wire. This is a loop of wire, but now in a magnetic field. The magnetic field, there is no force on the loop, but the loop tries to align in such a way that its plane is perpendicular to the magnetic field. A loop, this will be your design for a magnet. What a magnet does is just this. A magnet is nothing but a loop of current carrying wire. That's a model you can have. A magnet is only trying to have its current carrying loop in a plane perpendicular to the magnetic field. So it will try to turn around. Usually the magnets don't move around. That's for that you need a gradient of the magnetic field. We'll talk about this more. For now, I'll stop. Thank you.